All right, last example here. Again, we've got a rational function and we want to break it down into something that we can integrate. So let's first factor the denominator. So I see the difference of two squares here. So I can write that x to the fourth, because that's x squared squared, right? Minus 16, which is 4 squared. I can write that as x squared plus 4 times x squared minus 4. All right? And now I have another difference of two squares. So I can rewrite that. Let me just rewrite that down here. So I have 4x, oops, that's 4x cubed, isn't it? It should be a cube. 4x cubed. 4x cubed. And then when I get the denominator completely factored, I have this x squared plus 4, which can't be factored. It doesn't have any real solutions, right? If I tried to solve this, I get imaginary solutions. And then the x minus 4, though, is a difference of two squares. So that's going to be x plus 2 times x minus 2. Okay, so let's break it down into what we want it to look like. All right, I'm going to start with the linear factors just because they're a little easier to deal with. We know how to deal with linear factors. So we have a over x plus 2 plus b over x minus 2. And if you go back and look at that table, when we have an irreducible quadratic factor, the numerator looks like cx plus d. So we have a quadratic denominator, so we'll have a linear numerator. And so this is x squared plus 4. So I should say too that this actually, this method of reducing, partial fractions, the degree of the numerator has to be less than the degree of the denominator. If the degree of the numerator is greater than the degree of the denominator, then you have to use polynomial long division to modify the equation even more. We're not going to actually get into that. So all of these examples and the problems that you're going to do all have a numerator that has a degree less than the denominator. All right, so let's keep pushing forward here. All right, we're going to clear the denominators. So we're going to have 4x cubed, and then when I multiply the first term, I'll end up with a times x minus 2 times x squared plus 4. Okay, and then b, and the x minus 2's will cancel, so I'll have x plus 2 times x squared plus 4. And then finally, I'm going to have cx plus d times x plus 2, x minus 2. Okay, now it's just a matter of choosing some convenient values. So let's see, I'm going to start over here because I'm running up against that right edge. All right, so we have, let's see, it looks like minus 2, if I want to solve for a, minus 2 would be a good choice because that'll cause anything with x plus 2 to be 0. Right, so then everything will just, those are the b and c and d terms go away. All right, so I put in 2, and I'm going to have 4 times minus 8 is equal to a times minus 4, right, minus 2 minus 2. And then here I'm going to have 4 plus 4, which is 8. All right, well, that's nice. We have negative 32 on one side, negative 32 on the other side. So I'm just going to have a equals 1. All right. Now, the next one I probably want to choose is x equals 2, because that'll make anything with x minus 2 go away. And so I will end up with 4 times positive 8 this time equals, the a term will go away, and the c and d term will go away. So I'll be left with b times 2 plus 2 is 4, and 2 squared plus 4 is 8. All right. So that one comes out nicely too. B is just equal to 1. All right, now we still need to get C and D. All right, and there's nothing I can put into x squared plus 4 to make that go away. It's always going to be a positive number, right? I mean, anything squared is positive plus 4. There's no way I can make that into 0. So, but I can still choose convenient values. So let's try x equals 0. Okay, so then the left-hand side just becomes 0. And then I'm going to get, a times minus 2 times positive 4 plus b times 2 times 4, right? And then I'm going to have, now the 0 will make the c go away, all right? So then we'll be left with d. So I'm going to have, let's see, plus d times 2 times minus 2, right? All right, so, but we know a and b, right? A and b are 1, right? So this is equal to 1, and this is equal to 1. So I'll end up with a minus 8 plus 8, and those will just cancel each other out. So I basically have 0 equals minus 4d. And that means that, I'll write it over here, so it's d is equal to 0. Okay, well that's good. All right, we got D. Now we just have to get C. And I'm just going to choose another convenient value. And x equals 1 is a nice number to work with. So I'll end up with, on the right hand, or sorry, on the left hand side, I'll end up with just 4 times 1. And then I've just got to put everything in. So I have a times 1 minus 2, which is a minus 1. And then 1 plus 4, which is 5, plus b, and then I have 3 times 5, and then I'm going to have basically c plus d, but I know d is 0, and then this is going to be times 2 and times minus 2. Whoops. Hang on. I lost my train of thought there. All right, because I'm putting in 1, right? So I need to make this into 3 times minus 1, right? Minus 1. Okay, just plugging in 1. All right, now we know again a is equal to 1 and b is equal to 1. So I have 4 equals minus 5, and then plus 15 minus 3c, because d is equal to 0. And now I can solve for c. Okay, so this becomes positive 10. I subtract it from the other side, and I'm going to get 6 is equal to minus 3c, and so c equals 2. All right, well, we have everything we need now. So let's put this all together. Starting to run out of room. So we have the integral of, all right, so a was 1, so we have 1 over x plus 2. B is equal to 1, so we have 1 over x minus 2. And then we have 2x over x squared plus 4 dx. All right, so these first two are pretty easy to solve. In fact, I'll just write them down here. So we'll have the natural log of x plus 2 plus the natural log of x minus 2. And then we have to do it. This looks like a substitution problem to me. So I am going to say, let's see it, let u equal x squared plus 4. So du is equal to 2x dx. And then, so then you can see we've got a 2x in the numerator, and we can combine that. So we're essentially going to end up with the integral of 1 over u, and then this 2x dx becomes du. Okay, so it's just another natural log. So we have the natural log of x squared plus 4. All right, and then plus c. Now that one worked out nicely because we had a 2x in the numerator. Sometimes it doesn't work out quite as nicely, but that's, in this case, this is my final answer. Now, if I didn't have that 2x in the numerator, it's going to end up looking like an arctangent, right? Or the antiderivative of like a constant over x squared plus something. It's going to end up looking like an arctangent. So don't get complacent and think that every time you have something in the denominator, it's going to turn into a natural log. But anyway, that's my final answer. The next questions are all the discussion questions for you to practice on, and I'll see you in class.